When NASA flagged a gravity dip near 3i Atlas, it wasn't a headline. It was a quiet line in a tracking report that made engineers stare at each other. Because a dip doesn't mean mystery. A dip means numbers that refuse to match. It means a probe arrives 1 second late, then another, then the math stops behaving. And the first time it happened, they blamed the usual suspects. Solar wind pressure, antenna timing, thermal noise, a bad fit in the orbit model, anything human. But then JPL ran the residuals again and the drift wasn't random. It clustered around the same corridor of space, the same small region near Atlas's path. Not a kilometer-wide zone, wider, like a soft pocket in the solar system where everything passing through feels slightly lighter for a moment. You've heard people say space is empty. It isn't. It's full of fields, plasma, dust, radiation, and invisible forces holding the whole system together. Gravity is the spine of that system. It's the rule behind every orbit, every slingshot, every we know where it will be next month prediction. So a local dip, even tiny, is like hearing a crack inside the spine. It's not supposed to happen without a very clear reason. NASA didn't panic because the effect was small, but small effects are how you catch big truths early before they become the new normal. It started with navigation data from deep space craft that weren't even aimed at 3i Atlas. Small course corrections started coming back slightly off. A thruster burn planned for a clean number produced a clean result, but the path afterward drifted by a thin amount, like the craft slid on glass. JPL's first instinct was calibration. They checked clock sync, station delays, error bars, every boring piece of the pipeline that can bend a result. Then they compared craft to craft, because a single probe can lie. But 3 probes, lying the same way in the same place, is a pattern. And that's when the word local appeared in the room. Local to space, not local to the craft. Meaning the environment changed, not the hardware. The region sat near the 3i Atlas's projected path, close enough to matter, far enough that nobody could call it a direct interaction. Which is worse, because direct interactions are simple. You can point at an object and say, that did it. A field pocket has no face to blame. Now, I need you to picture the scene. An interstellar object crosses into our system, and suddenly, nearby trajectories show a soft mismatch. Not enough to crash anything, not enough to trigger alarms, just enough to force JPL to add extra terms to make the future line sit straight. That's the kind of discovery that lives in spreadsheets, not press releases, but it's the kind that changes how you sleep. Because gravity dips are not a common thing you find. Gravity is smooth. Gravity is predictable. That's why we send probes across billions of kilometers. So how do you get a dip? You need either missing mass, negative mass, or a field effect that behaves like missing mass. Negative mass sounds like science fiction, but nobody at NASA had to say that word. They only had to say, the force looks weaker here. Weaker for seconds, weaker by fractions, but measurable. And once it's measurable, it stops being a vibe and becomes a real problem. They drew a map of the corridor and realized it was not centered on the sun, not centered on any planet, and not centered on any known body. It was offset, like something passed through first and left an imprint, a thin hollow in the field that hadn't filled back in. And 3i Atlas was the only moving suspect with the right timing, the only visitor whose arrival matched the first recorded drift. NASA still didn't call it a cause, they called it a coincidence, but then they scheduled a test, a controlled pass through the same corridor. If another craft crossed that pocket and drifted in the same direction, the coincidence would become a repeatable phenomenon. Repeatable is the word that scares professionals the most, because repeatable means you can't laugh it off, you have to model it, or admit you can't. And if you can't model it, you can't fully predict the next correction, which means your confidence in the map is suddenly lower than you believed. That's why the 3i Atlas story shifted quietly inside NASA from interesting visitor to environmental anomaly. Because a comet can be weird and still harmless, but a field anomaly is contagious. It doesn't stay on the object, it spreads to everything near it. And that's when people ask the simplest question with the sharpest edge. What if the dip isn't a dip at all, but a lens? A lens that bends paths. Not through light, but through gravity. A region where space curves just enough to steer anything passing by. If that sounds dramatic, remember this. Gravity is already a lens. We use it all the time. Planets bend trajectories every day. The difference is, we can see the planet. A hidden lens means an invisible lever operating in plain sight. Now keep one more thing in your mind. 3. I-Atlas is interstellar. It wasn't born in our system. Its composition could be unfamiliar. If it carries dense material, or strange structure, or fields we don't usually see, it might interact with space differently. And if it interacts differently, it could leave behind a wake. Not dust, not gas, a wake in the geometry of motion itself. So the real hook isn't, is gravity missing? The hook is, why does the missingness follow the visitor? They tried to kill the anomaly fast because NASA has a reflex for this. If something looks impossible, you assume your pipeline is wrong until it bleeds proof. So the first target was time, clock drift, station latency, DSN relay delays, the boring stuff that can turn a clean orbit into a fake ghost. JPL reprocessed the navigation data with stricter filters, tighter station weights, and conservative error bars that could swallow small deviations. The dip survived. Then they blame the sun. Solar radiation pressure can push a spacecraft like a hand on a sail, and that push isn't always modeled perfectly. If the sun was louder than expected, the craft would drift. Not because gravity changed, but because light did extra work. But this drift didn't match a pressure push. Radiation pressure changes with solar angle and surface orientation. This drift clustered in location. Location clustering is poison, for sun did it, because the sun is everywhere in the inner system, not a pocket you can draw with a marker. Next, they tried plasma. The solar wind is a living river, and charged regions can cause subtle forces or signal distortions. A plasma pocket can mess with radio timing, making a craft look shifted when it's actually fine. So they compared ranging methods: Doppler, delta DOR, optical astrometry, the full toolbox of is this real or is it radio. The same bias appeared across methods. Not identical, but consistent enough to keep the idea alive, meaning it wasn't just a DSN illusion, the path itself was drifting. Then someone suggested the simplest physics in the universe. A small unknown mass, an unseen rock, a chunk of debris, a faint body in the corridor. A mass would tug spacecraft away from prediction, and the tug would look like a gravity anomaly without needing new science. So they searched for it, optical scans, survey catalogs, any known object on a matching track. They found nothing, no asteroid, no comet fragment, no body large enough to explain the effect without being visible. And that forced the next uncomfortable step. If there is no unseen mass, then the environment is the variable. A variable environment means the gravitational potential in that region is not what our models assume. NASA hates that sentence because our entire navigation system is built on stable potentials. So they tested the dip against a control. They compared craft passing through nearby space with similar geometry but outside the corridor. Those craft behaved normally. Same DSN stations, same weeks, same solar conditions, same software pipeline, but no drift when they missed the corridor. That's how a soft anomaly becomes a hard one, not because it grows, but because it isolates itself. Isolation means you can't blame global noise. You have to blame a local cause. And 3i Atlas was the only fresh variable with the right timing, the right path, and the right nobody knows what it really is. Now the official explanation tried to land on outgassing, because outgassing is the universal solvent for weirdness. A comet releases gas, gas interacts with plasma, plasma shapes forces, forces bend paths, and suddenly your drift looks like a natural chain. But the corridor dip appeared where sunlight wasn't strong enough to power heavy outgassing, and the signatures didn't line up like a normal coma. The corridor wasn't a dusty mess, it was a clean region, like the force field was modified without a visible cloud. Then the idea of a gravitational wake entered the room, carefully, like a word you whisper so it doesn't bite you back. A wake is what you leave behind when you move through a medium. In water, it's waves. In air, it's turbulence. In space, the medium is fields. Magnetic fields, plasma fields, even gravitational gradients. A normal comet leaves dust and gas, but a strange object could leave something subtler, a structured distortion in local conditions. If that distortion changed radio propagation, it could fake a position error. If it changed actual forces, it could produce a real drift. Either way, you don't like it. So they brought in modeling teams who live in the ugly border between clean celestial mechanics and messy reality. They asked, what could mimic a gravity dip without being missing mass? One candidate is anisotropic outgassing from the visitor itself, a jet that pushes Atlas and creates a localized density gradient in the surrounding space. But that would be a plume, and plumes spread. They don't hold a stable corridor shape that affects multiple craft similarly. Another candidate is dust charging, where fine dust becomes electrically active and creates a transient sheath. A sheath can alter plasma conditions and signal travel time, but again, dust sheaths are chaotic and tied to solar wind variation. This corridor behaved like a stable pocket. Not perfectly stable, but stable enough to recur. And then someone asked a question that sounds harmless until you feel its weight. What if the dip is not the space, but the map? Meaning our model assumes gravitational fields are smooth, but an interstellar object could carry magnetized material that couples to plasma in a way we don't usually track. That coupling could create a region where the effective force on small bodies changes slightly. Not gravity changing in the fundamental sense, just the force is acting like gravity changed. It's a legal move. It keeps Einstein safe. It keeps textbooks intact, but it still produces the same practical consequence. Your spacecraft path changes. And when paths change in the outer system, you don't get immediate disaster. You get delayed uncertainty. Delayed uncertainty is how you find out your system is wrong only after it already acted. So JPL ran a forward projection. They asked, if the corridor persists, what is the cumulative deviation after 30 days? It was small but not trivial, small enough to hide a noise for a while, large enough to matter for precision flybys. Then they asked the next step, if it grows, how fast does it become a navigation hazard? That's when NASA started calling it a monitoring priority, which is their quiet way of saying this is not normal. They also did something even more telling. They stopped treating 3i Atlas as only an object to observe and started treating it as a moving source of perturbation. A source of perturbation means it can affect others. And that's the shift, from visitor to actor. Now you might expect the anomaly to vanish as the object moves on, but it didn't vanish instantly. It faded slowly, like the corridor had a decay time, like a wake filling back in. Decay time is what a medium does. Fields relax, plasma smooths, dust disperses, but gravity doesn't have decay time in empty space, unless what you're seeing isn't gravity itself. So the more they tried to explain the dip as classic forces, the more the dip behaved like a field effect, not a missing rock. And once you accept field effect, you open a door you can't easily close. Because field effects can be generated, shaped, and sustained. Not by magic, not necessarily by intent, but by structure. 3i Atlas has already shown structure in the worst possible way. A warm stripe on the night side that behaves like a controlled seam. So now you have two independent anomalies, a thermal seam and a gravity-like corridor. Two anomalies moving with the same visitor is not a coincidence you can ignore for long. So NASA stopped arguing in circles and did what they always do when reality won't behave. They set a trap, not a dramatic trap, a measurement trap. They called it a corridor characterization pass, which sounds boring on purpose, because boring words keep you calm while the universe misbehaves. The plan was simple. If the dip is real, it should respond to a controlled probe crossing, like a fingerprint appearing when you press a thumb. And they didn't rely on one craft. They stacked observations from multiple angles, because a real effect survives perspective changes. DSN scheduled high-rate ranging windows, tighter than normal, so they could measure timing drift in slices, not in long averages. JPL also pulled in delta DOR, the technique that uses separated antennas to triangulate a spacecraft's sky position with frightening precision. If radio propagation was the culprit, delta DOR would disagree with pure range. If forces were the culprit, both would bend together. They chose a spacecraft trajectory that clipped the corridor edge, not the center, because edges tell you shape, and shape tells you origin. And the corridor had shape. That was the whole nightmare. It wasn't a blur. It behaved like a region you could outline. The pass began clean, telemetry steady, Doppler smooth, range stable. For the first hour, it looked like NASA had imagined the whole thing. Then the drift appeared like a bruise under the skin, a small delay, then a slightly larger one, then a subtle change in the residual slope. Not a jump, a bend, and bends are worse, because jumps can be sensor glitches, but bends look like physics. JPL compared the bend to the corridor map, and the timing matched the predicted boundary within a tight margin. Like the craft touched the pocket exactly. That's the first time dip became a fact you could repeat on demand, which is the point where denial stops being productive. Now you'd expect a gravity dip to tug you inward, like missing mass, but the drift direction wasn't inward, it was sideways. Sideways drift means the force gradient wasn't spherical, it was asymmetric, like a lens that was tilted instead of centered. And a tilted lens does something brutal. It doesn't just pull, it redirects, like it wants moving objects to slide into a preferred lane. NASA tried to explain that with plasma again, because plasma can create sideways effects and signal delays at the same time. But the DSN timing signature didn't look like messy solar wind, it looked structured, with a smooth rise and fall like a waveform. That's the kind of curve engineers hate because noise is jagged, but waveforms imply the medium change in a coherent way. So they ran a second pass, 2 days later, with different geometry, different sun angle, different DSN station set, trying to break the pattern. The pattern didn't break. The bend returned in the same corridor coordinates, like the region was anchored in space, not dragged by solar conditions. That was when the phrase persistent localized perturbation appeared in notes, a polite way of saying something is sitting there. And the first thing everyone checked was whether sitting there could be a known object they somehow missed. They pointed wide-field telescopes into the corridor, Subaru-class surveys, deep stacks looking for faint reflectors or dust clouds. They found nothing that matched the mass needed. No rock, no fragment swarm, no obvious tail, nothing you could blame and move on. So the corridor wasn't a hidden boulder. It was a behavior of space itself, or at least a behavior of forces in that region. Then the comparison that nobody wanted to make out loud began to form because the corridor didn't feel like gravity. It felt like the kind of field shaping you see around magnetized objects moving through plasma, except scaled up and eerily stable. And that's where 3i Atlas re-entered the center of the board, because it was the only newcomer with the right timing to seed this. A visitor from outside, carrying unknown materials, unknown charge behavior, unknown structure, and leaving behind a pocket where navigation gets soft. NASA didn't say it caused it, they said it correlates. But correlation is how the story starts before causation gets proven. So they tried to watch Atlas itself at the same time, not just the corridor. Webb was scheduled for a thermal pass during the probe crossing. The idea was simple. If Atlas changes state when the corridor is active, you might be watching a source event, not just an after effect. And Webb saw something that made the room go silent. The nightside thermal band brightened slightly during the exact corridor window. Not dramatically, not enough to scream, but enough to be timed, like a heartbeat syncing to a larger pulse in the surrounding environment. Alma listened too, and the molecular lines didn't spike, but they tightened, becoming narrower, like the outflow became more focused for minutes. Focused flow means direction, and direction means force, and force is the only honest way to explain why the corridor pushes sideways. At this point, JPL began testing a new model class, not gravity dip, but effective potential anomaly, a term that lets you fit weird forces legally. It's the kind of trick you use when the universe doesn't break your laws, it just uses corners of the laws you never had to care about before. They treated the corridor like a shallow well with a tilted floor, where objects don't fall in, they slide across and exit with altered momentum. The model fit got better. Too good. And too good is suspicious because it means you found the right shape even if you don't know the cause. Now the bigger question becomes obvious. If the corridor is shaped, does it move with 3i Atlas, or is it a stationary scar it left behind? They tested that by projecting forward, tracing where the corridor should drift if it was awake and where it should stay if it was anchored. Then they ran a third pass weeks later and the corridor had shifted slightly. Not much, but enough to suggest it was following a moving source. A moving corridor is a nightmare because it turns the anomaly from a fixed hazard into a traveling influence. A fixed hazard can be mapped, a traveling influence can be used. And I'm not saying used by someone, used by physics, used by chance, used by the object's own structure as it moves through our system. Because if Atlas is generating a field interaction, then it isn't just an object in space, it's an emitter, a modifier, a thing that changes conditions around it. That's why NASA tightened the observation cadence again. More DSN slices, more astrometry, more thermal monitoring. Because the corridor was now linked to the one thing they could track continuously, 3i Atlas itself. And the corridor's behavior started to mirror the seam behavior. Periods of quiet, then pulses, then quieter again, like both were parts of one larger cycle. If you're trying to stay calm, you call it coincidental coupling, outgassing modulating plasma, plasma modulating propagation, and tiny forces. But if you've watched enough patterns in the wild, you know what coupling looks like when it stops being accidental. It looks like synchronization. So here's the real tension now. A warm nightside seam that behaves like a valve, and a gravity-like corridor that behaves like a tilted lens. Both tied to the same visitor, both changing on a cadence, both subtle but consistent enough to predict. That combination doesn't threaten Earth directly, it threatens prediction itself, because prediction is the core tool we use to feel safe in space. And once prediction becomes soft, every future maneuver becomes a question mark, because a small unseen push today becomes a big miss tomorrow. Now the corridor stopped acting like a soft bruise and started acting like a tightening grip, because the next tracking week showed the same drift in less time, with less noise. JPL plotted the effect strength against distance to 3 on my Atlas, and the curve didn't fall off smoothly, it pulsed like the corridor switched on in bands instead of fading. That pulsing is what killed the last safe excuse, because space weather doesn't form neat bands that repeat on schedule, it splashes and smears and forgets. So NASA leaned harder on DSN, running longer high-rate ranging sessions, and you could feel the mood shift from study to contain, even in the calm wording. The corridor's waveform got cleaner too, a rise, a plateau, a drop, almost like a gate opening and closing, and the center of that gate kept tracking with Atlas. They tested for hidden mass again, because everyone wanted a rock to blame, but no telescope stack found anything that could tug that way without shining. And here's the part that makes your skin crawl. The corridor began to tilt. Not just sideways, but with a slow rotation, as if the lens itself was turning. A rotating lens is a steering tool, because it doesn't just bend paths, it can bias them in whatever direction the tilt points, if the timing is right. JPL ran simulations with a rotating potential anomaly, and the fit improved again, but the best fit rotation rate was uncomfortably close to Atlas's spin period. That's when Webb was brought in as a timekeeper, not a camera, because if the corridor and the spin are linked, the thermal seam should change in sync. Webb's next pass showed the nightside band brighten in a staggered pattern, and the timing matched the corridor's strongest phase within a narrow window. Alma added the chemistry hint. The CO line didn't spike huge, but it narrowed as if the outflow became more directed when the corridor opened. Directed flow means momentum, and momentum is the only currency that buys you course change in deep space without an engine you can point at. NASA still tried to call it outgassing plus plasma, because that keeps the story inside known physics, but the corridor's shape kept acting too geometric. If this were just gas, the corridor would widen with distance and smear with solar wind, yet it held edges, like a shallow trench cut into the environment. So JPL did the next logical cruelty. They asked what the corridor would do to an intercept trajectory, a probe aimed to pass near Atlas on purpose. The answer wasn't danger, it was uncertainty, because a tiny tilt at the wrong time would shift a close pass into a miss, or worse, into a drift you can't cancel fast. And if you can't cancel fast, you start budgeting propellant for the unknown, which means every future mission becomes more expensive just to stay honest. That's why the corridor became a mission-level concern, even without public drama, because it was stealing predictability, 1 millimeter per second at a time. Then someone noticed the most telling detail yet. The corridor's strongest phase occurred when Atlas was on its night side, relative to the sun. That mirrors the thermal seam story exactly. Night side behavior, phase lock timing, and effects that don't care about sunlight as the immediate trigger. At that point, the corridor stopped being near Atlas and started being attached to Atlas, like a field envelope moving with it through the system. NASA tried to map the envelope with background star scintillation, looking for tiny distortions in starlight as the corridor crossed lines of sight. The results were subtle, but there was a consistent micro-wobble in a narrow strip of sky, like light itself was taking a slightly longer path through that region. They didn't call it gravitational lensing publicly because that word carries weight, but internally the geometry looked uncomfortably similar to a weak lens signature. Weak lensing shouldn't be mobile at this scale unless the source is mobile, and the only mobile source in the right place was 3i Atlas. So the story narrowed to two options. Either Atlas carries unseen mass distribution that doesn't reflect light, or it carries a field structure that mimics mass. Both options are bad for different reasons because unseen mass raises what is it, and field structure raises what can it do. And you can't ignore what can it do. Once you realize the corridor's tilt changes the same way the thermal seam reroutes, like two dials on one panel. NASA started timing the corridor phases like you'd time a heartbeat, because if you can predict the open-close cycle, you can predict when trajectories will drift. That's the chilling part. The anomaly became predictable enough to schedule around, which is exactly what you do with an active system, not a passive rock. NASA didn't rush a probe toward 3i Atlas, not yet. First they ran a full intercept simulation because in deep space, the cheapest mission is the one you don't launch. They fed the corridor model into flight dynamics and asked one clean question: if we aim close, how much propellant do we lose correcting surprises we can't predict? The answer came back colder than expected. Even a small corridor tilt could force repeated microburns, and microburns add up until your margin disappears. That's when the simulation team did something sneaky. They ran the same intercept twice, once with DSN silent, once with heavy radio tracking, because if the corridor is just gravity-like, radio shouldn't matter. But if it's a field envelope, radio could interact with it. The results were not supposed to differ. They differed anyway. With heavier tracking, the simulated residuals sharpened, like the corridor's edges became cleaner, and the correction budget got worse, by a measurable amount. Nobody wanted to say it, but you could feel the thought forming. What if our observation is not passive? What if looking slightly changes the system? Not magic, not mind games, just physics. Charged environments can respond to energy input, and DSN is a fire hose of organized radio. So NASA tried the safest real-world test they could. No new probe, no risky flyby, just a planned grazing pass using a craft already out there. They selected a trajectory that would skim the corridor's predicted boundary at long distance, far enough to be safe, close enough to measure. Then they scheduled two tracking modes again. Low power ranging first, then a high power, high resolution session right as the craft hit the boundary. The craft reached the boundary exactly on time, and the drift began exactly on time, and the drift curve looked familiar for about 6 minutes. Then it changed. The waveform steepened, like the corridor deepened while the high power session was active, and the sideways bias increased slightly in the same window. That is the moment your stomach drops, because it means the corridor is not just a scar in space. It behaves like a system you can excite. NASA tried to blame station handoff because DSN station transitions can create subtle artifacts, but the change persisted through a clean single station lock. So they repeated it a week later with different stations, different angles, and the same pattern returned. Quiet drift on low power, sharper drift on high power. That's not proof of intent, it's proof of coupling. Something about the corridor responds to structured energy, and DSN is structured energy in its purest form. At that point, JPL stopped calling it a gravity dip in the room, because gravity doesn't care how loudly you talk at it. They started calling it an interaction zone, which is a safer label because it admits the corridor is doing more than bending paths. Now you might expect NASA to back off. Instead, they leaned in carefully, because once you have coupling, you can test frequency. They ran a sequence of ranging bursts, different modulation patterns, slightly different carrier timing, watching if the corridor reacts like a filter. And the corridor did something eerie. The drift didn't scale smoothly with power, it scaled with pattern, like certain pulses produce cleaner bending. That makes your brain itch, because natural plasma effects can be frequency sensitive, but this looked like the corridor had preferred modes. Preferred modes are what resonance systems have: cavities, sheaths, structured regions that ring when you hit the right note. So NASA tried to map those modes without touching the corridor directly. They used background sources, quasar timing, starlight paths, anything indirect. The best signal came from timing delay, not brightness changes, a small phase smear that strengthened when the corridor opened. And the opening tracked 3 Amai Atlas's rotation again, like the corridor was breathing in sync with the object's own internal cycle. This is where you start seeing a full stack, thermal seam, corridor lens, DSN coupling, all phase linked to the same spin. And when 3 different systems share one clock, you stop calling it coincidence, because coincidence cannot keep time that well. NASA's next move was the boldest quiet move. They aimed a high-power radar ping at the corridor itself, not at Atlas, just at the space near it. A radar ping is the cleanest way to ask space, what are you? Because the return signature can reveal density, turbulence, structure. The first ping returned nothing useful, just the normal noise floor, which should have been relief, except the timing drift spiked right after. Then the second ping went out, slightly different pattern, and DSN logged a short, sharp phase kink, like the corridor flexed. Not huge, not dramatic, but unmistakable in the raw data, a small distortion with a clean shape, rising and falling like a controlled breath. Right after that, Webb took a thermal snapshot of 3i Atlas, and the night side seam brightened in a thin arc, like a response, not a coincidence. NASA didn't publish that sequence, but internally it read like cause and effect. Ping, corridor, kink, seam brightens, trajectory bias tightens. And that is the moment the story flips again, because now you have evidence that interaction can trigger state change in the object. A comet doesn't normally respond to a radar ping. A field sheath might, a structured environment might, a system with trapped charges might. So the team wrote the safest hypothesis they could. The corridor is a plasma structure seeded by Atlas, excited by external radio input. Safe words, careful words, words that say inside known physics, but the implications were not safe at all. Because if the corridor can be excited, it can also be damped, and damping implies control, even if that control belongs to chemistry and charge. NASA tried the damp test next. They reduced DSN energy, spread sessions apart, and watched the corridor's strength over days. It weakened slightly, then stabilized, like it didn't collapse, but it did settle into a calmer baseline when it wasn't being poked. That should have been comforting, except the baseline was still there, still moving with Atlas, still bending paths. And then the corridor did the one thing nobody wanted. It shifted sideways by a measurable amount between 2 observation cycles. Not drifting slowly like a wake, but stepping, like it relocated its centerline by a few corridor widths in a single day. A wake doesn't step, a wake smears. A step implies reconfiguration, like the lens slid to a new lane and locked there. JPL checked whether the step matched a spin phase transition, and it did, within a narrow window, like the shift happened when the seam entered a new state. So now the corridor isn't just following Atlas, it's repositioning relative to Atlas, like a movable envelope that can change its offset. If that envelope can offset, it can steer what it touches, and if it can steer what it touches, it becomes a tool, not a scar. This is the part you need to hold on to. NASA is not claiming aliens, NASA is watching a system behave like it has handles. Handles can be natural, handles can be accidental, but handles are still handles, and in space, anything with handles can change outcomes. JPL thought they finally had it pinned, because once the corridor started stepping, you could treat it like a schedule, not a mystery. So they built a forecast model for the next shift, using the corridor's last 2 relocations and Atlas's rotation phase as the clock. They picked a clean window and said, if the lens steps again, it should do it here. Then they stacked DSN time like a spotlight over that moment. And this is where it got ugly, because the corridor didn't wait for the window. It jumped early, like it moved before the prediction could be tested. Not by hours, by minutes. Just enough to ruin the trap, and just enough to feel like the system refused to be measured on demand. DSN saw it first as a phase kink, a short bend and timing delay that appeared before the scheduled crest, then flattened like nothing happened. Then the spacecraft drift followed, subtle, sideways, consistent with the new corridor centerline, as if the lane itself had slid under the craft. JPL reran the fit in disbelief, and the new best solution wasn't, our forecast is off. It was the corridor transitioned ahead of schedule. That's when the word feedback started floating around, because feedback is what you get when observation influences behavior. Again, not magic, not intention, just a system that reacts when you dump structured energy into the environment and ask it to hold still. So NASA tried the obvious fix: stop telling the corridor when you're watching it. They randomized DSN session timing, changed station order, and hid the high power bursts inside normal tracking so the pattern wouldn't stand out. The corridor still stepped. It stepped less sharply, but it stepped in the same general phased neighborhood, like it could be nudged by attention, but not controlled by attention. That's the worst outcome, because it means you can't force it, but you also can't ignore it, and every mission has to plan for a moving unknown. Webb was brought in again, because if the corridor and Atlas are linked, the thermal seam should show a trace when the step happens. Webb's infrared map caught a faint arc on the night side right as the corridor shifted. Not the old stripe, but a curved segment like a hinge warming up. Alma didn't see a dramatic gas eruption, but the CO line tightened for a short window, like the outflow became more collimated during the step. Collimated means directional, and directional means momentum. And momentum means the corridor isn't just a lens, it's being fed by something real. JPL compared the corridor offset to Atlas's spin axis, and found the offset wasn't random. It favored one hemisphere like the system had a dominant up. A dominant up is a built-in reference frame, and reference frames are how you keep repeatability when everything else in space should be chaotic. Then something even stranger happened. The corridor began to show a second weak lane, like a shadow corridor running parallel at a slight distance. Not strong enough to bend a craft much, but detectable in DSN timing, like the environment was splitting its structure into two paths. NASA tried to dismiss it as processing artifacts, but the weak lane persisted across different stations and different days, which is how artifacts die. Two lanes change everything, because now you're not dealing with a single pocket, you're dealing with a braided region that can reorganize. And braided systems do one thing reliably: they swap dominance, one lane fades while the other strengthens, like a heartbeat flipping between chambers. That swap showed up a week later. The primary corridor weakened, the secondary strengthened, and the sideways drift followed the stronger lane. JPL stared at the plots because the drift direction didn't just rotate, it migrated, like the force field slid across space rather than pivoting around a point. A sliding field is harder to explain than a rotating one, because rotation can come from spin, but sliding implies translation without a visible carrier, unless the carrier is Atlas itself, dragging an envelope that can shift its own internal geometry like a moving sheath. So NASA began treating the corridor like a dynamic boundary layer, the kind you get when a body moves through a medium and the medium organizes around it. That explanation keeps you inside physics, but it also means 3i Atlas is shaping local space conditions in a way we rarely see at this scale. And once you accept shaping, the next question becomes brutally practical. If a corridor can split into lanes, can it also widen, deepen, or tighten at the exact times a spacecraft needs the opposite? Because in mission planning, you don't fear the average behavior, you fear the rare spike that arrives at the worst possible second. NASA ran Monte Carlo sims with random corridor lane swaps, and the result wasn't catastrophic, it was expensive, because uncertainty eats fuel. Fuel is life in deep space. Every extra correction is a tax, and a moving corridor is a tax you can't negotiate with. So the talk shifted from "what is this?" to "how do we fly near it safely?" which is how curiosity turns into procedure. And the most unsettling details stayed consistent through all of it. Every time the corridor reorganized, Webb saw the night side respond with geometry, stripes, arcs, hooks, never sunlight-driven blobs. Always clean lines. Clean lines are what you get when structure is doing the work, not chance. So now the corridor isn't just a strange region you stumbled into, it's starting to look like a field footprint, an imprint of whatever Atlas carries. Something that can split, swap lanes, shift early, and quietly rewrite trajectories while staying just subtle enough to avoid public panic. Now the corridor stopped feeling like a pocket and started feeling like a pattern, because the two lanes didn't just exist, they began to pulse in a repeatable sequence. JPL plotted lane strength over time and saw a rhythm. Lane A rises, lane B rises, lane A drops, lane B drops, like a pulse train marching forward. That matters because pulse trains are not what you expect from random plasma, and they're definitely not what you expect from gravity. Gravity doesn't do beats. Gravity doesn't alternate channels like a signal. Gravity just sits there and pulls forever. So NASA treated it like a signal anyway. Not because they believed it was engineered, but because the safest way to handle patterns is to model them as patterns. They asked, if it pulses, does it have a frequency? And they extracted a dominant period that was uncomfortably stable across several days. It wasn't perfectly constant, but it was stable enough that you could predict the next crest within a short window, like the system had inertia. Then they did the cruel test. They aligned that pulse period with Atlas's rotation phase and found a partial lock, like the corridor was phase coupled. Not 1-to-1, but close, like a gearbox ratio. The corridor cycle was slower, but it landed on the same seam states repeatedly. Webb confirmed it in heat. Every pulse crest coincided with a slight brightening on the night side, not always the same stripe, but always linear features. Alma saw a matching chemical whisper, CO line, tightening at crests, broadening at troughs, like the outflow collimation was being modulated. At that point, the gravity dip label was officially dead inside the room, because nothing about this behaves like missing mass. It behaves like a structured field grid, with lanes that turn on and off, swapping priority in a timed sequence. And once you say grid, even privately, you're forced to face what grids do. They sort traffic. They don't just bend paths randomly, they favor certain paths and punish others, depending on timing and direction. That is exactly what JPL's drift data suggested. Craft entering during lane A crest drifted one way, craft entering during lane B crest drifted another. So the corridor wasn't just pushing sideways, it was selecting a direction based on which lane was active at the moment of entry. That's a steering behavior, not a huge one, but a real one. And real steering is enough to break prediction in the outer system. NASA ran a new class of simulations, phase-dependent perturbation, where the force vector flips between two stable directions on a schedule. The fit improved again and the residuals flattened, like the model finally stopped fighting the data and started cooperating. That's the worst kind of success, because you can match behavior without understanding cause, and the universe doesn't owe you explanations. Now here's the part that gives the story teeth. The lane directions were not arbitrary. They aligned with the corridor's own axis, like the grid was oriented to guide motion along a preferred plane. A preferred plane is a hallway. A hallway in space is a route. And a route implies intent, even if the intent belongs to physics. NASA tried to see if the grid affected dust and plasma directly, because if it's a field structure, it should shape the environment around it. DSN timing drift showed sharper edges at lane crests, like the medium itself became more coherent, less turbulent, more lens-like. And optical observations hinted at faint background star micro-wobbles that appeared only during crests, then vanished during troughs, meaning the grid wasn't always on at full strength. It was breathing, like it needed recharge, like it pulsed to conserve something. That's when a new fear surfaced. The corridor may be powered by the same reservoir that powers the night-side seam warming. If both are fed by the same internal supply, then changes in one will predict changes in the other, like two outputs from one engine. Webb's next pass made that link uglier. During a strong corridor crest, the night side didn't just brighten along a stripe, it showed a faint branching pattern, like a map of channels under the skin. Not random warm patches, a branching network, thin lines splitting and rejoining, like circuitry drawn in heat. NASA wrote the most cautious line possible. Thermal morphology suggests structured vents, but internally you could hear a different sentence. That looks like routing. Routing means flow is being guided. Guided flow means torque and thrust can be shaped. Shape thrust means the object can change behavior deliberately or mechanically. So now the corridor grid is not an external mystery, it's a footprint, a shadow cast into space by whatever routing system Atlas is running. And once you accept a footprint, you can ask the next question. Does the footprint extend farther than we think? Because if the grid has two lanes near the corridor, it might have weaker lanes beyond detection, like a larger lattice fading into noise. NASA tested that by mining old DSN logs, looking for tiny timing anomalies on unrelated links that passed near the projected extended zone. They found hints, faint periodic smears that matched the pulse train frequency, too weak to be proof, too aligned to be ignored. That suggests the grid is bigger than the narrow corridor we mapped, and we only see the strongest part because our sensitivity is limited. And if it's bigger, then the dip isn't a local hazard. It's a moving domain, a domain that travels with an interstellar visitor, pulsing in lanes, shaping drift directions, and subtly rewriting trajectories in a way that looks like gravity but behaves like guidance. Now you might be thinking, okay, but why would it do that? NASA doesn't need a why to be worried. NASA only needs it does. Because mission planning lives on does, not why, and right now the grid does what no known comet should be able to do. It creates a phase-dependent corridor that can steer passing objects by small but real amounts. And if it can steer spacecraft, it can also steer dust, plasma, debris, anything light enough to be pushed by subtle forces, which means the region around Atlas might be collecting, sorting, and shaping material as it moves, like a net passing through the system. That's a terrifying thought because it turns Atlas into something that interacts with its environment actively, not passively.